So, hi, I'm Yu, and today I will talk about near linear size hypergraph cut sparsifiers. And this is a joint work with Sanjeev and Ansh. So let's first define what is a cut sparsifier. Given a graph G, a cut sparsifier G prime is a sparse graph that preserves all cut values G within a factor of 1 plus or minus epsilon. So for example, if in the original graph, there are 5 edges crossing the cut, then in the sparsifier, there might be only 2 edges in the cut, but the weight might be 2 and 3, and such that the cut value is preserved. So the quality of a cut sparsifier is the number of edges in it. And the classic result by Benjamin-Carger shows that any graph has a 1 plus or minus epsilon cut sparsifier that contains n log n over epsilon square edges. So in this work, we consider the cut sparsifier in hypergraphs. So let's first review what is a hypergraph. A hypergraph is a generalization of standard graph where a hyperedge may contain more than 2 vertices. And then the value of a cut is the total weight of the hyperedges crossing the cut. Now, given a hypergraph H, a cut sparsifier H prime is a hypergraph that preserves all cut values in H within a factor of 1 plus or minus epsilon. So let's first review what is known about the size of hypergraph cut sparsifier. Kogan and cross grammar shows that any hypergraph has a 1 plus minus epsilon cut sparsifier that contains n times r plus log n over epsilon square hyperedges, where r is the maximum size of hyperedge, and it is computable in polynomial time. So note that r could be as large as order n. So this is the upper bound of n squared over epsilon squared in general, so which is almost a factor of n larger than the bound for standard graphs. So in this work, we prove that any hypergraph has a 1 plus minus epsilon cut sparsifier that contains only n log n over epsilon squared hyperedges, and it is also computable in polynomial time. Note that it matches the result of Benjamin-Carger for standard graphs. And moreover, our algorithm can be converted into a streaming algorithm. So as a corollary, we prove that there is an insertion-only single-pass streaming algorithm that computes a sparsifier with n log n over epsilon squared hyperedges, which uses n squared over epsilon squared space. Note that just to store these edges, we need this many space. So in the remaining of talk, I will describe the main idea of our work. So let's first briefly review the framework of Benjamin-Carger for cut sparsifier in standard graph. In a graph, a k-strong component of a graph G is a maximal vertex-induced graph of G that has mean cut size at least k. And then the strength of an edge E, we write by ke, is the maximum value k that E is contained in a k-strong component. So a well-known result shows that the summation of WE, which is the weight of E over KE, which is the strength of E, is smaller or equal to n minus 1. And the definition above can be directly applied to hypergraphs. And the bound given in the lemma also holds for hypergraphs. So Benjamin-Carger proves that given a graph G, if we sample each edge E with probability about log n over epsilon squared over times ke, then the resulting graph G prime is a cut sparsifier of G with n log n over epsilon squared edges. Now, there is a key step in the algorithm called cut counting bound, which shows that given a graph G with minimum cut size C, then the number of cuts in G with size at most alpha times C is at most n to the 2 alpha. And this means that if alpha is a constant, the number of such cuts is polynomial, which allow us to use the union bound to prove the concentration of all cuts. And Kogan and cross grammar used exactly the same framework of Benjamin-Carger, but the main change is that the cut counting bound in hypergraph is much larger. They show that Given a hypergraph H with minimum cut size C, then the number of cuts in H with size at most alpha times C is at most 2 to the 2 alpha times R plus log n. So as a result, they prove that if we sample each hyperedge with probability R plus log n over epsilon squared times Ke, then the resulting graph is a cut sparsifier, and it has order nr over epsilon squared hyperedges. So to improve the size of a hypergraph sparsifier, a natural idea is to try improving the cut counting bound. But it turns out that the cut counting bound is almost tight, so maybe we need a new approach. Well, in our approach, we create our sparsifier by creating an auxiliary graph. So we first convert each hyperedge to a clique, and then distributing its weight over the edges in the clique. For example, if a hyperedge E has 5 vertices, then we convert it into a clique contains 5 vertices, and we call that Fe. We call the resulting graph auxiliary graph. And at a high level, our approach is to couple the analysis of cuts in hypergraph with cuts in the auxiliary graph, so that we can rely on the cut counting bound in standard graph. As it turns out, the coupling requires that all edges in the clique representing a hyperedge have similar strengths. So to ensure this, we may assign non-uniform weights to the clique edges. However, it may not be always possible, but it is sufficient to ensure that any clique edges with positive weights have the strength similar to the minimal strength edge in the clique. Let's formalize the idea. So we define kappa E equals the minimum strength in the clique Fe, and kappa E max be the maximum strength of positive weight edges in the clique Fe. And then we call a weight assignment scheme a balanced weight assignment. If in each Fe, the sum of weight of FWF is 1, and the ratio of kappa E max over kappa E is at most 2. And given a balanced weight assignment, we set PE approximately log n over epsilon squared kappa E, which is equals to log n over epsilon squared sum of Fe WF over kappa E. And by doing so, the expected size of the resulting graph is summation of PE, which is roughly log n over epsilon squared times summation of F with WF over kappa E, which is approximately log n over epsilon squared summation over F WF over KF. This is because for any edge F, if WF is larger than 0, then we have KF is similar to kappa E. And if WF is 0, then WF over kappa E is 0, and we didn't need to care about this term. And in the end, the size is about order n log n over epsilon squared. So this concludes the main idea of this work. But to prove the scheme correctly outputs a hypergraph cut sparsifier, we need to do the following 2 tasks. First, we need to prove that balanced assignments always exist in hypergraph, and we can always find one in polynomial time. And second, we need to prove that any balanced assignment gives a valid cut sparsifier. And this follows by modifying the framework of Benson-Carger. So in conclusion, we show that every hypergraph has a sparsifier with order n log n over epsilon squared hyperedges. But note that if each hyperedge has size r, then the space used by our sparsifier is order nr. So one may ask if there exist data structures that can approximately answer cut queries using that space. But very recently, Kaparov et al. Shows that any such data structure actually requires almost nr space. So the space used by our sparsifier is optimal up to log factors. So that's it. Thanks for listening. Hello?
Okay, thank you very much for the talk. Are there any questions? You can just unmute and ask, or you can write them in the Slack channel.
Question.
Ask a question?
Okay.
Was there a question?
Yeah, I have a question. So how important is the 2 in your definition of balanced assignment? What if, can it be any constant and you're still okay?
Yeah, that's true.
And 2 is the smallest constant for which there is a balanced assignment?
Oh, actually, we proved that there exists a balanced weight assignment even if it is 1. So which means kappa E max equals kappa E. But this might be not, I don't know if it's computable in polynomial time. So we just prove it exists. But for any 1 plus epsilon, we can find such one in polynomial time, also in epsilon.
Thank you.
Yeah.
There's another question in the chat. What is the running time for the construction?
The running time is about m times n square. Well, m is the number of hyperedges and plus something like n to the 10 over epsilon to the 7, I think. Yeah. Yeah, but if m is very large, then the first term will dominate the remaining.
I also have a question. You said it's the corollary is that it gives you an algorithm for insertion only streaming.
Yeah.
Can you do something to get it for insertion deletion? What would you need?
I don't know if we can do insertion and deletion, because insertion streaming algorithm is actually use some standard ideas we can do. So I don't know if we can also do deletions. Yeah.
Okay, then if there are no more questions, we can go to our next talk.
Okay. How do I stop sharing the screen? Wait. I can't find how to stop.
Okay, let me see if I can do it.
Yeah.
Okay, now I will stop sharing and hopefully. Okay, Zihan, can you share?
Sure. Yeah, does that work?
Yes. Great. Okay, so the next talk is by Zihan Tan, towards better approximation of graph crossing number.
Okay, thank you for the introduction. I'm presenting our work towards better approximation of graph crossing number. And this is based on joint work with my advisor, Julia Chijoy, and Zebedee Mahabadi, both from TTIC. And I think both are in the audience. Okay. So the graph crossing number is a well-known problem in graph theory and graph algorithms. And its input is simply a graph. And the goal is to compute a drawing of the graph in the plane with minimum number of crossings. Okay, so what do we mean by drawing? We simply draw vertices as points and draw edges as curves connecting points that corresponds to the endpoints of the edge in the graph. Okay, and the crossing is simply an intersection between a pair of curves. So for example, we take a graph G equals K4, which is a complete graph on 4 vertices. Then this is a drawing of K4 in the plane. And in this drawing, we have 1 crossing. And in fact, we know that K4 is a planar graph. Okay, so if we draw it in this way, then we obtain a drawing with 0 crossings, which is also known as a planar drawing. Okay, so the crossing number of a graph is defined to be the minimum number of crossings in any drawing of G. And in this graph crossing number problem, the goal is to compute this number, compute the CRG, and also a drawing that achieves this many crossings. So it's a famous problem, and what is previously known on this problem. So it was introduced in 1940s by Paul Turin, and since then has been studied extensively. So according to a bibliography maintained by Virtil, by 2014, there are already 700 more papers on this topic. But despite being studied extensively, our understanding towards this problem is still far from complete. So for general graphs, there's no non-trivial algorithm for just a non-trivial approximation algorithm for general graph. And in fact, any approximation algorithm whose approximation ratio will depend on the max degree of the graph. So, but the hardness result, best hardness result is only APX hard. Okay, so not much is known for the general graph. But we do have one beautiful result about the combinatorial result, which is this crossing number inequality. So this inequality says that if the number of edges is larger than 4 times its number of vertices, then the crossing number must be of order at least m cubed over n squared. Okay, so this inequality basically tells us that if the graph is dense, then it must have large crossing number. So the interesting part of this problem is really when the graph is sparse. And therefore, it makes sense to look at the bounded degree graphs, which is also the main research directions on this topic in the past 10 years. So what is previously known on bounded degree graphs? So I should note that in this slide, when I'm presenting some approximation ratio, I'm ignoring the dependence on the max degree of the graph, which is bounded by a constant. Okay. So the first algorithm came from the famous paper by Layton and Rao on multi-commutative flow and sparseness cut. Okay, so they show that they can compute a drawing. With n plus DRG crossings. Okay, and which translates into a ON approximation. And later on, it was improved by 2 papers that shaves off some log factors. Okay, and meanwhile, the best hardness result is only APX hard. Okay, so very recently, well, not very recently, 10 years ago. So by a sequence of 2 papers, first by Chujoy, Makarchev, and Sidiropoulos, and second by Chujoy, they managed to improve the approximation ratio to n to the 0.9. Okay, and later on, by 2 more recent papers, they improved the approximation by Kobayashi and Sidiropoulos. They improved the approximation ratio to square root of n. Okay, so in this work, we further improved this approximation ratio to n to the 0.5 minus epsilon, where epsilon is something like 1/80. Okay, so this seems like a slight improvement on approximation ratio, but we believe that the more important contribution is that our results use a different framework, use a different algorithm that paves a way towards much better approximation. So just to be a little bit more specific here, all previous results that is presented on this slide use the same framework for their algorithm. And it has been proved that this framework cannot give better than square root of n approximation. And what we did is that we introduced a new framework that overcomes this barrier by eventually providing a better than square root of n algorithm to illustrate that. Okay. And it turns out by using this framework, we reduce the crossing number problem to a similar one, but seemingly simpler one, which is called the crossing number with rotation system problem. Okay, so I will introduce this problem later. So this is our main result. So now let's first look at what are the previous framework that is used by all the previous work on this, well, in the recent 10 years. So the framework is actually kind of simple, and it is also indeed the framework that is used in all kinds of heuristics. So the first step is to compute a planarizing edge set E of the given graph, where by planarizing edge set, we mean a subset of edges. If we remove these edges from the graph, then the remaining graph is planar. Okay. So the first step is to compute a planarizing edge set, and the second step is to compute a drawing of the remaining graph, which that we remove the planarizing edge set from. Okay, and the third step is to add the edges back to the drawing. Okay, so for example, if we take a graph which is K5, we know that K5 is not a planar graph, but the planarizing set can simply contain any edge of a K5. And for example, this is a drawing of it's a planar drawing of K5 minus 1 edge. And in this framework, the third step is basically to add the missing edge back. And in this way, we'll obtain a drawing of K5 with only 1 crossing. Okay, so I'm not going into the details of how the previous work indeed how they use this framework. But the best algorithm, the best result that it can show is that we can obtain efficiently drawing with CRG squared crossings using this framework. So if the given graph has crossing number CRG, okay, and this translates into a into the 0.5 approximation, which is also the best known so far. And it has been proved that for every integer k, there exists a graph with crossing number k, and it also contains a planarizing edge set with only k edges, such that any drawing of this graph that induces a planar drawing of G minus E prime must contain at least k squared crossings. Okay, so basically this CRG squared is the best we can hope for in this O framework, and therefore the best approximation ratio is also square root of n. So we want to break this barrier. We need to basically come up with something new. So our new framework is kind of a modified version of the old framework. It consists of 4 steps. So the first step is still to compute a planarizing set E prime. In fact, we can use the algorithm proposed in Kobayashi and Sidipoulos paper in 2019 that computes a planarizing set with sides approximately CRG. But then we allow ourselves to augment this set a little bit by adding additional edges to it, such that we get a E double prime set, and its size is still approximately CRG. And also G minus E double prime has some additional properties, which is a combination of weakened 3-vertex connectivity, bridge connectivity, bridge property, and bounded well likeness. So I'm not going to the details of these properties. And the third and fourth step are still are identical to the second and third step in the old framework. So we compute a planar drawing of G minus double E double prime, and then added edges of E double prime back to the drawing. Okay, so does this small change even help? So what we show is that it does. So we show that we can compute efficiently a E double prime such that there exists a near optimal drawing with approximately CRG crossings in which only the edges E double prime participate in the crossings. Note that this is stronger than saying that G minus E double prime is planar, because that is equivalent to saying that every crossing involves at least one edge of E double prime. And here we're saying that we require that every crossing involve both edges. They're both from E double prime set. So yeah, and the second result is that after using the first theorem to obtain a set E double prime, implementing the third and the fourth step is equivalent to solving an instance of crossing number with rotation system problem. And we come up with an algorithm that can get a better than CRG, that can get CRG 2 minus epsilon crossings for a small epsilon. So this seems, so just by combining theorem 1 and theorem 2, we obtain an n to the 0.5 minus epsilon approximation. Okay, so or just briefly explain what is a crossing number with rotation system problem at the end. So its input is no longer not only a graph G, but also for each vertex a circular order, or we also call it a rotation of its incident edges. Okay, and its goal is to compute a drawing of G that respect these circular orders, by which I mean for each vertex, all its incident edges, their images must enter this vertex in the given circular order. So for example, this is a drawing that satisfies, that respects all circular order. So is this problem simpler or harder? So on one hand, on the positive side, we know the rotation on each vertex, so it seems very useful information. But on the other hand, the graph, the input graph is not necessarily bounded degree. So we already, although we cannot prove rigorously that it is simpler, we tend to believe that it is. So previously known result for this problem is a n to the 4 approximation, even in the even special case that the orientations are also given. Okay, so the flip status of the clockwise ordering is also given. And what we did is that we can get a drawing with the number of edges plus the number of the crossing number to the 2 minus epsilon prime crossings. Okay, note that the number of edges crossing, number of edges square crossing is kind of trivial. So what we did is we pushed down the exponent 2 by 1/20. Okay, so this is our result. And combined with the main theorem 1, this gives a n to the better than square root of approximation. Okay, so summary is we give a better better approximation algorithm using a new framework. And the main future direction is still to either get better approximation or prove stronger hardness for this problem. And it can be done by a better approximation algorithm for this new problem, crossing number with rotation system. And that's all I'm going to say. Thank you.
Thank you very much for the talk. Any questions? Okay, so the question is, there's a question in the chat. What is the next natural approximation ratio barrier?
Next approximation ratio barrier. So actually, it is an ongoing work, and probably, sorry, am I still sharing the screen? Anyway,
no.
Okay. Anyway, sorry. So it's an ongoing work, and I'm probably not supposed to say much about it, but we are, I think, optimistic that we can get much better approximation compared with the current one. And yeah, believe the correct approximation ratio should not be any polynomial of n. So yeah, it should be better than that. Maybe not strictly polylogarithmic, but yeah, it should be better than any polynomial of n. So, but that's just my weak belief of this. Yeah, still an ongoing work.
Thank you. And there's another question. Is there a lower bound for the approximation ratio for this problem?
For which problem? The crossing number problem or the crossing number with rotation system? So yeah, actually for both of them, the best hardness result is only APX hard. Yeah, but this strong result also holds for very special case. For example, the graph is bounded degree. Even for bounded degree graph, the hardness result is APX hard, but this is the best we know so far.
Okay, thank you. I think I don't see any more questions, so we can go for our next talk.
So Talia, I guess I will have to give the next talk because my co-author Jason Lee was supposed to give it, but I can't track him. So I'll actually give it. So I'll double up as administrator and speaker. But should we wait till 11:30 before we start?
Sure. Yes, let's wait a minute. You can start sharing for now to see that everything is okay.
Is my screen visible?
Yes.
Let me know when you want me to start.
Let's wait a minute. Yeah. Okay, I think we can start.
Right. So thanks for coming to the session. I'm Dhammalia Panigray. So I was, my co-author Jason Lee was planning to give this talk, but I can't track him, so he might have gotten times mixed up. So what I'll do is I'll give this talk, but I'm giving it off slides that correspond to a much longer talk that I gave a few days back. So I'll zoom through some of the slides to try and fit it in the 10-minute format. So this is joint work with Jason, as I said, from Carnegie Mellon. And we are going to talk about deterministic algorithms for the min-cut problem. So what's the min-cut problem? I'll actually go over this very quickly. This is something that many of you are familiar with. So given a graph, I want to find the smallest cut in the graph, namely the smallest set of edges whose removal disconnects the graph. And in particular, we are going to look at graphs that are that can have edge weights, in which case we are looking for the cut with the smallest weight, or could have parallel unweighted edges. But it can't have directions. So so everything that I talk about is only for undirected graphs. So another sort of component of our discussion today would be the ST min-cut problem, which is also a very common problem. So here it's exactly the same problem as earlier. The only difference is that now I also specify two vertices called terminals S and T, and I want to find the smallest cut that disconnects S from T. So I'm no longer looking for the smallest cut globally, but the one among the cuts that disconnect S from T, I'm looking for the smallest one. So it's been known for many years that the ST min cut is the dual of the max flow problem, the ST max flow problem. And that's one way of solving ST min cuts. And that was what got people started on the min cut problem. You can solve min cut by just running ST min cut for all pairs of vertices. And then there were a sequence of advances until the early 90s, when we got a flurry of algorithms that run in time m times n. And I'm going to suppress the polylog factors in these running times. M is the number of edges, n is the number of vertices. One particular algorithm among these that is worth mentioning is an algorithm due to Howe and Orlin. So what this algorithm does is it shows that instead of running a bunch of different max flows to compute, or a bunch of different ST min cuts to compute a min cut, you can actually amortize these times, the max flow running time, so that overall you are effectively running only log n max flows. But the catch was that this only works for a specific max flow algorithm, in particular the push relabel algorithm of Kohlberg and Tarchin. And that was indeed the best max flow algorithm of the time. So that's the bottom line. We were at mn time, and that's where we were stuck for about 20 years. Now, since then, there have been many advances in ST min cut algorithms, because there have been advances in max flow algorithms. And currently, the fastest running time that we know of for the ST min cut problem, even using deterministic algorithms, is something like m to the 4/3. Okay, so that's much faster than could be faster than mn. And the question that we are asking is, can we actually solve min cut using polylog max flows, irrespective of which max flow algorithm you use? That will certainly help us translate these gains in the max flow algorithms to the min cut problem as well. Now this is the view for deterministic algorithms. Things moved randomized algorithms, and there were several algorithms. Eventually, there was an algorithm in the mid-90s given by Kargar that solves min cut in Monte Carlo m time. So it's a near linear running time. It's m polylog n. All of these are Monte Carlo algorithms, which means that there's some probability that you are not going to get the right answer. And even if you went for Las Vegas algorithms, running times are slower. Okay, so that gives us another open problem. Can we solve min cut deterministically, or even Las Vegas in near linear time? So those were the two problems that drove our research. And indeed, there was no progress on these till about 5 years back, when a remarkable paper of Kawarabayashi and Thorup gave a deterministic near linear time algorithm for min cuts, but it works only for simple graphs. In a rather strict sense, the algorithm is not correct if you apply it to non-simple graphs. So it's not just that the running time becomes worse. But it's still, this paper contains a lot of, a wealth of ideas that are useful for us. And then there was a simplification of this, and the running time was also improved in the logarithmic factors by Hensinger, Rao, and Wang. But for weighted or multi-graphs, for general undirected graphs, the mn time from the early 90s remains the best before our work. So our main result is that we can show that we can reduce the min cut problem to polylog and max flows. And the additional time we take outside these max flow subroutines is about linear. So it's m raised to 1 plus epsilon for an arbitrarily small epsilon. So that resolves the first open question and makes some progress towards resolving the second one. So I'll quickly go over our main idea. So our main idea is something called isolators. Isolators are, this is an idea that is possibly useful outside the min cut problem. And in fact, we have been trying to use it for various other problems. So it's worth going over this. And then I'll talk a little bit about how isolators are used in this context. Okay, so what's an isolator? So suppose let's say there's a min cut that separates the vertices S from the rest of the vertices. An isolator, we define an isolator as a subset of vertices such that it has exactly one vertex on any one of the two sides of the cut. Okay, so the set itself can have any arbitrary number of vertices, but it must have the property that it hits one of the sides of the cut at exactly one vertex. It could be any of the vertices on that side, but exactly one of them. If you give me such a set, I call that an isolator. Okay, so let me keep going. So that's the vertices I've circled in green is an example of an isolator set. And our main lemma, technical lemma that makes the entire paper work, entire result work, is that we show that if you give me an isolator, then in fact I can find you a min cut deterministically in log t max flow calls where the size of the isolator is t. Okay, so the isolator of course cannot have more than n vertices. So in general, we are going to give you the min cut back in log n max flow calls. Okay, so this is something that's important, is that the dependence of the number of max flow calls on the number of vertices I gave you in the isolator is logarithmic, and that's where it's non-trivial. If this were polynomial, obtaining something like this is not so hard. So I'm not going to prove this lemma, I don't have time, so I'll just skip over to the next part where we talk about how to use this lemma. Okay, so first let me give you a very quick randomized algorithm. So I know that we are looking for deterministic algorithms, but just to show you the power of isolators. So recall that we have a min cut. Now one thing we can do is we can guess the size of S, right? There are only log n guesses up to a factor of 2. And then we can just sample at the right rate. So 1 over the guessed size. And with constant probability, we will hit exactly one vertex on one of the sides of the min cut. So simply by doing this log many times over these log different levels of guesses, we can ensure that one of these different sets that I'm generating in the samples is going to be an isolator. So all I do is I just take these log n different levels of sampling. At each level, I sample a bunch of times, let's say log n times. That gives me a set of maybe log squared number of sets. I know one of them is an isolator with high probability. So all I do is now run my isolator lemma in all of these sets, and whichever is the smallest cut the isolator lemma returns, that's the one I return. So that's a very simple randomized min cut algorithm once you believe the isolator lemma. But note that we are looking for deterministic algorithms. So this is the part that gets a little technical, and I'll give you a sketch in 2 or 3 minutes. So there are a few ideas that go into this. The first one is that we extend the idea of isolators slightly. In particular, we call a set an almost isolator if instead of hitting exactly one vertex, you can ensure that the overlap with one of the sides of the min cut is polylog n. So the overlap isn't large, but it's not as precise or as small as just a single vertex. And our first claim is that once we are given an almost isolator, we can in fact deterministically generate a list of subsets where we will have an isolator among those sets. Okay, and this is deterministic. So with probability 1, we are going to, I mean, there's nothing random going on. We are going to indeed have an isolator among that list. Okay, and how do we do this? Let me skip the details, but basically we implement a beautiful idea of Alan Euster and Zwick called color coding. So they used it in a different context, but we are able to use it in the current context to generate this list of potential isolators given an almost isolator. So that's the first idea. That reduces our problem to obtaining an almost isolator. If we're able to obtain an almost isolator, then we are done. And the last piece of the puzzle is how do we get to an almost isolator? So we show this lemma where we say that if you don't have an almost isolator, so if you have a subset of vertices that overlaps both sides of your min cut at more than polylog n vertices, then in fact you can do a sparsification. This is not sparsification in the sense of the first stop where you want to reduce the number of edges, but here I want my set of vertices in this isolator that I'm trying to build, I want that to become smaller, but I want that to become smaller while still overlapping both sides of the min cut. Okay, so we show that if your overlap on the smaller side is larger than polylog n, then in fact you can come up with a set that's half in size that still overlaps both of the sides. So you can keep doing this until you find an isolator. And of course, you don't know when you find an isolator, so you just run your isolator lemma on all of these candidates. Okay, so how do you do this? So again, I will skip the details. But basically, the idea is we use something called a deterministic expander decomposition due to Chuzoi, Gao, Li, Nanongkai, Peng, and Saranurak. So the basic idea is if I can split up my graph into a bunch of expanders, then my min cut cannot really cut very deep into these expanders, because then it's incurring a lot of edges if it's cutting deep into the expanders. In the ideal case, the min cut will actually not cut into any expander at all. And if that happens, then in what we were suggesting, the sparsification is very easy. We just pick one vertex from each of these expander sets. Okay, and if I pick one vertex from each of these components, then I know that I'm covering both sides because my cut is not cutting into any of these components. And we sort of generalize this a little bit. This is strictly not true in general. The min cut could cut into expanders, kind of glance through some of these expanders. So you need to pick a few more vertices and cover for that. So that's all I have to say. The most important open problem is to get to a near linear time deterministic in cut algorithm, most important problem in the context of this paper. And we have also been successful recently in using the isolator lemma in other contexts for connectivity problems, and we hope to see more applications of the lemma in the future. Thank you very much.
Great. Thank you very much for your talk. Unfortunately, I think we have only time for one question.
One quick question. So do you compute the expander decomposition repeatedly, or is it done only once?
Just once. Yeah. Well, I mean, just once for each round of sparsification.
I see. Thank you.
Okay. And there were actually more questions in the Slack channel, so please, if you can address them later.
Sure. Thank you.
We can prepare for the next talk. Do we have our next speaker?
Yep.
Okay. Great. Thank you. Okay, you can go ahead and start.
Okay, cool. So this talk is about the faster mean cost flow algorithm in graphs with unit capacity. So it's joint work with Alexander Matry and Adrian Vladu. So what's this problem about? We're given a directed graph, and for each vertex of this graph, we're given a demand. Now, we want to find a flow that satisfies this demand, meaning that for each vertex, we want the amount of flow exiting this vertex minus the amount of flow entering this vertex to be equal to the prescribed demand on the given vertex. So for example, this is a flow that satisfies the demand, and you can see that in the top left vertex, for instance, the amount of flow exiting is 2, the amount of flow entering is 1. So 2 minus 1 is equal to the prescribed demand, which is 1. Furthermore, we also add capacity constraints to this. Basically, for each edge, we want the flow on that edge to never be negative and to never exceed 1. And here is a flow that satisfies both of these constraints that we have set. So these constraints already capture the max flow problem, but we're gonna go ahead and make it more general by adding a cost, introducing a cost to the problem. So for each edge, we have a cost, which basically means how much we pay for each unit of flow that we route on this edge. So here the red edges have cost 1 and the green edge has cost -1. And we basically want to find a flow that minimizes this cost. And here is such a flow. You can see, for instance, that this min cost flow has chosen to avoid the red edges because they're more expensive and to choose the green edge instead because it's cheaper. So, but why do we care about this problem? For one, it has a lot of special cases. We could say it's the mother of graph problems. For example, max flow, negative weight shortest path, and min cost bipartite B matching are all special cases of this problem, and they are important problems on their own right. And also another important thing is that it gives us a pathway to more generally understand interior point methods. And there have been a series of works that get a refined understanding of interior point methods by getting faster algorithms for the min cost flow problem. So let's see how fast we can solve it. This problem has been studied since the 50s, and there have been a lot of different algorithms and bounds. And currently, the fastest known for sparse graphs is m to 10/7 log w by Cohen, Madry, Sankovsky, and Vladu in 2017. And in this work, we improved this bound to m to 4/3 log w. And furthermore, this also implies faster algorithms for related problems like negative weight shortest path and min cost bipartite B matching, where the L1 norm of B is OM. So let's take a high-level view of the previous approach for this problem. They start from the initial min cost flow instance, which they reduce to a bipartite matching instance, again with costs. And then they apply an interior point method on that instance. And whenever there is not enough progress in the interior point method, they perturb a few high energy edges. And then finally, they repair the solution to get the solution for the original problem. The first step of our approach will be to get rid of the reduction. So we're going to work directly on the initial instance, which will give us some better understanding since we'll be working on the instance that we actually want to solve. So let's look more specifically at what our formulation will be. So we would like to minimize the cost of a flow. And I will explain in a second what AX is here, but C is the cost vector, and this is the inner product between the cost vector and the flow. And we have the capacity constraints. So F0 here is an arbitrary fixed initial flow that satisfies the demand D. And AX will be a circulation that we add to this flow in order to preserve the demand, but also minimize the cost. And more specifically, what is A here? A is a matrix that is edged by cycles. And basically, its columns are cycles of the graph. So it's easy to see that any vector of the form AX is a circulation of the original graph, meaning that it has demand 0. But if we pick the cycles carefully, we can also guarantee that any circulation can be written as AX. So I will not go in depth on how we do this, but here is an example in which we pick various cycles of this graph. And if you look at it carefully, basically any circulation of the graph can be written as a linear combination of the columns of A. Okay, so now we have our linear program. And of course, we're going to solve it with an interior point method. And the usual way to do this is to replace the constraints by log barrier terms. So this now is an unconstrained log barrier problem. And note that we additionally have an extra parameter mu, which is in the linear term. And we eventually want to solve this unconstrained problem for a small enough value of mu. So more specifically, each step of the method will proceed as follows. We have an optimal solution for this problem. And we want to find an optimal solution for the same problem, but for a smaller parameter mu. So we have a mu prime to be mu over 1 plus delta, and we want to find a solution for this problem. Now, more specifically, we can think of this step as computing and augmenting circulation. So in each step, basically, we have some suboptimal flow, and we basically define an optimization problem, the optimal solution of which will give us the augmenting circulation that we will push on this flow. So in this sense, it is compatible with more traditional combinatorial algorithms. Now, the interesting part about this augmenting problem is that it is approximately quadratic, meaning that we can roughly think of F tilde as an electrical circulation. And here delta is a step size, and R are the resistances that will define this electrical circulation. And one result that we will use is that, in fact, this approximation, this quadratic approximation to V of F is actually good enough as long as the energy on each edge is at most 1 over 100. And the energy is given by resistance times flow squared. So as long as this property is true, we can actually compute the augmenting circulation in near linear time. So now the whole game will be what is the step size that we can set so that we can make sure that the energy on each edge is small. So how to control this energy? Now the standard bound is as follows. Bounds the energy of an edge by the total energy of the graph. It's a very simple bound, and it directly leads to an m to 3/2 algorithm for this problem. However, there are some caveats with this approach. Basically, it doesn't take the connectivity of the graph into account at all. So, for example, if you have two vertices and let's say m edges that connect them, let's say m parallel edges, each with resistance R, well, then the energy will be equally distributed between these m edges. So this means that the energy of each edge will be 1 over m fraction of the total energy, meaning that this bound can be like 1 over m wrong, basically. Can be off by 1 over m factor. In contrast, we have a different approach that does take connectivity into account. So we again bound the energy of each edge, but now by a different quantity. So in the numerator, we have the step size that we have chosen. And in the denominator, we have a quantity that we call the weighted conductance. So this is like the conductance, but it's weighted by some appropriate weights. More specifically, phi is the minimum over all cuts of the graph, S. And in the numerator, we have the sum over the edges of the cut of 1 over root resistance. These are the weights. And in the denominator, we have the volume of S, which is a usual thing. So this is we count once the number of edges in the cut and twice the number of edges inside S. So now let's see what we can do with this, this new bound. And as a matter of fact, we can see that if we combine this with another recent approach, which has been used in the context of flows, which is the LP regularization approach, we can fairly easily get an m over root conductance log W algorithm. So that's nice. We have a new algorithm, but the problem is that it depends on this conductance quantity that we're not sure how to lower bound. And it's not clear whether it does have a lower bound. So what we will do is we will have to enforce it. And the way we do this is by also adding a star regularizer to the graph. This is like basically we're adding an extra star on the graph, as well as a quadratic objective, as a quadratic regularizer on the objective. And it turns out that after balancing the amount of perturbation introduced and the value of phi that we get an m to 4/3 log W algorithm. So to recap, we have an m to 4/3 log W algorithm for unit capacity max flow, mean cost flow. And important observation is that weighted conductance turns out to be important for interior point method convergence. Some follow-up questions are whether we can increase the conductance but without introducing artificial demand. Artificial demand is the perturbation that we introduced. And another question is whether we can increase conductance for more general LPs. And the big question, I think, in this problem is whether we can get logarithmic as opposed to polynomial dependence on the capacity so that we can solve this problem for general capacity. That was all.
Thank you very much. Great talk. Any questions? Okay. Okay, so no more questions. You can get ready for the next talk by Ohad Trabelsi about cut equivalent trees that are optimal for mean, which are optimal for mean cut queries. Okay, so let's wait a minute to start. And Noat, can you bring the presentation to present mode?
Hi, can you hear me?
Yes.
Okay.
But we see the present, not the present mode.
So can you see the, wait a second.
No. Great.
Yes, okay.
Yes. Great, so let's wait a minute. Okay, you can start.
Thank you very much. Thank you everyone for being here. I'm going to talk about the paper cut equivalent trees are optimal for mean cut queries. And this is joint work with Amir Aboud and Robbie Kraugammer. So the topic of this lecture is the all pairs max flow problem, or all pairs mean cut. In this problem, we were given a graph, and we need to output for every pair of nodes the maximum flow that can be shipped between them. We are going to look on the data structure and the static versions of this problem. Now, let me remind you that the maximum ST flow and the minimum ST cut have the same value by the max flow mean cut theorem. And also, the current upper bound for the single pair version is m squared 10, where m is the number of edges and n is the number of nodes. And there are some faster algorithms in special cases. So the naive approach to solve our problem is to run the single pair max flow m squared times. And 60 years ago, Gomery and Hu showed how to reduce this problem to trees. So what they showed is that it is possible to construct a data structure of linear size that answers minimum cut queries quickly. And this data structure is in fact a tree on the same set of nodes as the given graph, so that the minimum ST cut in the tree is also a minimum ST cut in the input graph. And this tree is called a cut equivalent tree. And note that there is also a weaker notion that is called the flow equivalent tree that only preserves the flow values rather than also the cuts. Note also that there could be at most n-1 answers. Now, the cut equivalent trees are a great solution because the query time is very fast and the space complexity is linear. They are very elegant. But what about the construction time? So in the general case, it takes n-1 applications of max flow. And there are some fast algorithms in special cases, not in particular the unweighted version. So there are a few open questions at this point. The main one is it possible to construct a cut equivalent tree faster than n applications of max flow? And another one is it possible to get a data structure with faster pre-processing time than cut equivalent trees, a data structure that might not be a tree? And finally, maybe these two questions are actually the same question. So now let's talk a little bit about conditional lower bounds. So first, in the directed case, we know that there could be n² answers. And currently, no known algorithm can compute the all-pairs max flow faster than the naive approach of solving for n² pairs separately. Now, the conditional lower bounds are for a single source, all sinks version, and the all-pairs max flow. The lower bounds are n² and n³ respectively, assuming the 3 orthogonal vectors conjecture, and that's also ACTH. And for dense graphs, there is a conditional lower bound for all pairs max flow of n to the omega plus 1, where omega is the fast matrix multiplication. And this is assuming a different conjecture, which is the Forkley conjecture. Now back to our questions. So these conditional lower bounds don't tell us much because they deal with directed graphs. So the main question remains, are these two questions the same? So one direction is simple. If we want to reduce the all pairs mean cut data structure to the cut equivalent tree construction, then in the paper we show that by a simple reduction to two-dimensional range queries that it is simple. But the other direction is not clear. And a main result of this paper is that yes, so a cut equivalent tree can be constructed in near linear time, if and only if there is a mean cut data structure with near linear pre-processing time and polylogarithmic query time. And this is even if the queries are restricted to a fixed source. So there are some corollaries here. So the first one is that for the family of bounded tree-with graphs, we now know that the cut equivalent trees can be constructed in near linear time. And to do that, we use a mean cut data structure from 98. And this was not known before. And there is a similar consequence for planar graphs, but this was known before, however, using different techniques. Now, the way we show this is by this cycle of reductions. So the single source mean cut data structure can be trivially reduced to the all pairs mean cut data structure. And the all pairs mean cut data structure can be reduced to the cut equivalent tree construction. This is the simple reduction that uses the two-dimensional range queries. And the reduction between the cut equivalent tree construction and the single source mean cut data structure is the main contribution here. The second result that we have is about approximations. What we show is that given a capacitated graph on n nodes, one can construct 1 plus epsilon approximate flow equivalent tree in roughly n² time. And note that this is almost tight if the graph is dense or if all pairs need to be reported. So to conclude, For the approximation, we have the mean data structure and the n-squared flow equivalent tree. And the open question is, can we get an approximate cut equivalent tree rather than just a flow equivalent tree and the mean data structure? And also, is it possible to have a near linear time algorithm as opposed to the m-squared, which is almost tight for the dense case? For the exact case, we show that faster Gomory-Wood tree algorithm can happen if and only if there is a faster mean cut data structure. So the main open question, is it possible to break the algorithm by Gomory and Hu from 60 years ago that showed how to construct a cut equivalent tree and applications of max flow? So it is still open whether it is possible to have an n to the 0.99 applications of max flow, or even for the unweighted version, n to the 2.99 time algorithm. Another question is it possible to have conditional lower bounds for these problems in undirected graphs? And in a new and very exciting result, we showed, which is currently under submission, we showed we showed how to design an algorithm with running time n to the 2.75 for the construction of cut equivalent trees in unweighted graphs. That would be it. Thank you.
Great. Thank you very much. Are there any questions? So we have a question from David. If does the new algorithm rely on a sublinear number of max flow applications?
The new algorithm, you mean the new algorithm, the new result, or the algorithm in this paper?
The unpublished work.
Sorry?
Ohad, I was asking about the new unpublished work.
I guess it is hard to say whether it is about a certain amount of max flow applications. The graphs are different, and the whole framework is. We can take it offline if you want. Discuss this.
All right, sounds good.
Okay.
Okay. If there are no more questions, then we have a few minutes until.
Could I ask a question?
Sure.
Yes.
Hi. So just to make sure, on your last slide, could you just go back to the last slide?
Yes, of course.
So this, like the first one, even for the approximation part, there's really nothing better known than n max flows, right? It's just that here you can run max flows in linear time by sparsification and approximate max flows.
Yeah, so we show an algorithm that is arguably more robust than the Gomory-Hu framework that can actually use the faster algorithm for approximate.
That's right, but it's still n max flows, approximate versions of max flows on sparsified graphs.
Yes.
Okay. Yeah, just wanted to clarify that. Thank you.
Okay, thank you for the talk. I think we have a few minutes to the next talk, but we can start the screen sharing.
I'm giving the next talk. Could I share my slides or something like that?
Good. Let's wait a minute. So.
I'll be back in 1 second.
Okay, we're about to start with the last talk of this session by Yang Liu about unit capacity maximum flow in almost m to the 4/3 time.
Thanks for the introduction. Hi everyone, I'm Yang, and I'm going to be talking about improved algorithms for the maximum flow problem. This is a merge of two papers, paper of Aaron and I, and the paper of Tarun. To get started, I want to remind everyone what the ST max flow problem is. In this problem, we have a graph G with n vertices, m edges, and every edge is a directed edge with a capacity U. And our goal is to send flow from S to T such that the flow on every edge is at most its capacity and satisfies a couple of other demand conditions. Precisely, we want to ensure that for every vertex, which is not S or T, that the total incoming flow equals the total outgoing flow. And our goal is to maximize the total amount of flow exiting S, or equivalently entering T. This is a long studied problem that has been studied for a long time. There's several applications. It implies algorithms for ST cut, bipartite matching, scheduling problems, and recent advances in max flow have often led to new algorithms for mid-cost flow or optimal transport. In general, it's a very simple, structured optimization problem, and therefore, when new techniques on it have led to very general techniques for even problems beyond max flow. And yeah, just in general, anytime there's been an improvement to max flow, it's been applied in other settings, such as even regression problems. And it really gives us a good place to down new optimization techniques and see how they look. As for what's been known on the max flow problem, there's been a long line of work. Today I'm going to focus on the setting of sparse graphs that are unweighted. So in this chart, this is the algorithm of Madri 13, Madri 16, and recent work of myself and Sidford. These algorithms are in time m to the 10⁷, or the improved one is m to the 11⁸ in the case of sparse unweighted graphs. To get a feeling for where these exponents are coming from, this exponent 10⁷ is 3/2 minus 1/14. Here 3/2 is the classical runtime. 11⁸ is 3/2 minus 1/8, and 4/3 is 3/2 minus 1/6. So as I've mentioned, our main result here is that we give an algorithm for unit capacity max flow that runs in time m to the 4/3 plus little o of 1. And this implies an algorithm for bipartite matching in the same time m to the 4/3 plus 1. There's also a separate paper in this conference that gets runtime m plus n to the 3/2 for bipartite matching. And also we get the same runtime m to the 4/3 for the minimum ST cut problem. At this point, I'm going to dive straight into what an interior point method is, which is what we use to get our algorithm, and what is our key differences between our method and previous interior point methods. An interior point method, as set up by Madri 2016, is kind of the following. At every single time, we're going to maintain a flow f, which routes v units from s to t. We're also going to maintain some forward weights and backward weights on the edges. So an edge is bidirectional. There's a forward version and a backwards version. We're going to maintain w plus and w minus on those two. The algorithm looks at the following potential function. It looks at the minimum weighted log barrier. So what it does is it maintains minimizers of the following function. Over all flows that send v units from s to t, minimize negative the weighted sum of log of ue minus f and ue plus f. The way you should think about this is ue minus f is the residual forward capacity, and ue plus fe is the residual backwards capacity. So to minimize this function, you're really ensuring that the flow isn't getting too close to saturating either of the forward or backward constraints, while it routes exactly v units from s to t. So how do we use this potential function to actually route more and more units of flow from s to t, like an augmenting pads algorithm? We do it as follows. Once again, we track this potential. And let's say that currently we have a flow that minimizes this and routes v units from s to t. Our goal now is to route delta more units from s to t while still being a minimizer of instead of v at v plus delta. The interior point methods generally do this via something like a progress step, where they add some electric flow, some ST electric flow, that will send us from the minimizer at v to the approximate minimizer at v plus delta. Then the method applies a recentering step, which takes us from an approximate minimizer at v plus delta to an exact minimizer at v plus delta by computing some more electric flows or circulations to. This method generically gives a root m convergence, like it takes root m steps to get to a high accuracy solution. And every step takes m time, so that total times m to the 3/2. So how do we improve? Well, there's some magic steps where you essentially you change the weights to reduce the iteration complexity. I'm going to get into this a little bit at the end. So on this previous slide, I said we wanted to advance from v to v plus delta. So our goal is to set delta as possible to ensure that we can actually efficiently move from the minimizer at v to the minimizer at v plus delta. So there's a couple important things that you need to guarantee this. The first thing is that when I'm adding this induced electric flow, I need to make sure that I'm not violating any capacity constraints. Normalize this is you define the congestion vector as value of flow I want to add on an edge divided by the residual capacity. Then as long as the infinity norm of this congestion is at most like something like 0.1, then adding the flow will not change any residual capacity by more than a constant factor. And therefore, we can add it successfully. However, when you're using electric flows, because you're not exactly moving to the next minimizer, because you're only moving to a proximate minimizer, turns out that you actually, instead of controlling the infinity norm of congestion, you're forced to control the L4 norm of congestion. And this results from the fact that the electric flow is only approximating the step from the minimizer V to V plus delta instead of exactly. So kind of a takeaway is that it's hard to actually use electric like this dream dependent infinity and instead get this rho 4 norm. And we say get this rho 4 norm that we need to depend on. And at a high level, this is actually why the previous algorithms of Maudry and Lewin Sidford had trouble improving over their respective bounds of m to the 10.7s and m to the 11.8. It was because they had to control this 4 norm very precisely. So given all of this, the way to improve is that we're actually just not going to use electric flows to take off ending steps. We're just going to directly move between V, the operator V and V plus delta, using this thing we're going to call a divergence minimizing flow. So essentially, we're just going to say, instead of augmenting by electric flow, we're just going to send delta more units. And the delta units are a flow that would send us exactly from the minimizer at V to V plus delta. To define this flow, we're going to use the KKT conditions and set up some Bregman divergence problem. More precisely, let's define this log barrier, or like this potential function phi. Then the KKT conditions say that if you have a flow f, that it minimizes this if and only if by equals the gradient of phi. So this is, well, just again, this condition exactly characterizes what are the central values, or like what are the flows that are minimizers of this function. It's flows f that exactly satisfy by equals the gradient of the potential function. So our goal is we're given a flow and y such that by equals the gradient of f, and f sends exactly v units. Now we want to send v plus delta units from S to T and add some new flow f hat and some dual y hat to exactly satisfy the centrality condition for the next value. To do this, we're going to set up this Bregman divergence problem. Min B transpose f hat equals delta chi st of the Bregman divergence. The way this relates to the electric energy is that the Bregman divergence, the second order approximation, is actually equal to the electric energy, which is where the electric flow earlier comes from. This is because when you do the Bregman divergence, it's defined to just take the function and subtract out the first two orders of like the Taylor expansion. So you're left with a quadratic, and that's where the electric flow comes from. But like the Bregman divergence is the full problem, which means that we're not actually losing anything. More precisely, if you just write out the computation, then you write out the KKT conditions for the Bregman divergence problem. You get that by hat equals the difference of the two gradients. Then if you add them, you get that the flow f plus f hat is exactly central for y plus y hat. And because this point is exactly central, this allows us to, instead of controlling the 4 norm of congestion, to just focus on controlling the infinity norm of congestion for this new divergence minimizing flow. And then you can kind of plug through the same method of Lewin Sidford that got the m to the 11/8 algorithm and get an m to the 4/3 algorithm out of this. So to conclude, what we gave is an improved algorithm for unit capacity max bipartite matching in time m to the 4/3. The key point is that an electric energy, which was used in previous algorithms, is a second order approximation of a more complicated expression, this Bregman divergence. So if we computed this exactly or more directly, then we never need to leave this central path recenter. Therefore, we can focus on minimizing infinity normal congestion instead of L4. And you can reduce this L infinity normal congestion using weight changes via the framework of Lucid for that got the 11/8 to the 11/8 algorithm. Yeah. As for what are further things to do here, I think it would be interesting to give a more direct m to the 4/3 time algorithm that uses some of the machinery in the algorithm here. Additionally, are there further applications? There's been a couple, I think. For example, you can get a min cost flow algorithm that runs in time m to the 4/3 out of this. And finally, our algorithm only works for unit capacity graphs. Can you get an algorithm that works in time m to the 1.49 that depends logarithmically on the capacities? I would be happy to take any questions.
Thank you very much. Any questions?
I have a question. Can you hear me?
Yes, I can hear you.
Can you hear me? Okay. So what happens if you have the high order norm oracle stuff that's undirected, so the P norm. What happens if I get like some other versions of that? Like, are there like other ways of tweaking that oracle? Like, for example, going to a, I guess directed would already give you some kind of that, like that would just, what would happen? I guess directed would be too strong of a tweak as well, but are there like other like intermediate oracles that would be useful for this type of things?
So the question was, underlying this algorithm, we use some high-powered 2 norm plus LP norm flow oracle, and the question is whether we know of any oracles that seem similar to that would give an improved runtime. So I guess the thing is, we don't know how to get any improved results if you assume even a weighted version of that. So that oracle only works for unweighted. For even a weighted version, we don't know how to get any improvements. Directed is too strong because approximate directed max flow implies exact directed max flow trivially. No, in full, I don't know.